Hi guys, I hope you are well and are doing okay. It's Mr. Longley here, and we're going to be starting an algorithms module and a computational thinking module. This is a absolutely fantastic module. We usually do it in year 9, but we're going to be starting you off early, and then we'll be coming back to it later on. This module is really interesting because it actually makes you more of an intelligent person. So, for instance, computational thinking is used in your everyday lives. It's breaking down problems, and people want to employ computer scientists because of the way they think. And yes, computer scientists can code, but not every single computer scientist career you go into is through coding. It's actually through your logical thinking and breaking down problems. So, like for instance, I was a systems analyst and business analyst. I was used for my thinking skills and to be able to break down problems. I'd used to walk down the factory floor and go, right, we need to do this, this, and this to save the company money. People employ computer scientists just to look at the stock market and look for trends in data and stuff like that. With computational thinking, it will also make you much more intelligent in other subjects such as science and English and maths. Because we're breaking down problems all the time in our every single day lives. And by applying computational thinking and logical thinking, you'll find that if you master it, you'll be much better in other subjects too. So let's get into the module. Today, we're going to be going over just some basic definitions and applying some computational thinking tasks and stuff like that. And then as the weeks go out, we're going to be learning the steps taken in some really famous algorithms and that we use today. And we're going to start looking at how people create these algorithms and the steps they take in order to do that. So we're going to introduce the fundamental computational thinking techniques today. We're going to be defining abstraction and decomposition, and we're going to be completing some computational thinking activities. But what I'd like you to do beforehand, I'd like you to play Articulate with someone in the house, just for a minute. So you've got 60 seconds, and what I want you to do, Articulate is basically you describe items. So for instance, it has a mouse and a keyboard, it has a screen, it runs software and applications. You're probably thinking of a computer. And if your partner says computer, then you get a point, and it's how many points you can get in a minute, basically. So, for instance, it's got 4 legs. People sit on it. You would say chair. You can't say the word. You have to describe it, and then they have to name it. So you've got see how many the person you can name in 60 seconds. So pause the video, time yourself 60 seconds. Off you go. Okay guys, welcome back. So by doing that, you was actually applying computational thinking, and you were applying computational thinking techniques to describe and break down various aspects and descriptions of objects around the house. And so Articulate is a real world example of computational thinking. All right, well, throughout this module, what we're going to be doing is we're going to be writing down a couple of notes. So if you have your books with you, fantastic, write the notes in your book. If you don't have a book with you, if you've got a pad and paper, that's also fine, but you will need some kind of writing material to write down all of these notes. Okay, so let's have a look through. So computational thinking is about taking a complex problem and being able to use several computational thinking techniques: abstraction, decomposition, pattern recognition, and algorithmic thinking to fully understand the problem and then create a solution to it. So let's say you've got a problem where you need to create a system for an entire school, then that's a huge, massive problem. If you apply these 4 computational thinking pillars, then you will be able to understand what you need to do and then also create a solution for it. So we're going to go into detail in all of these pillars just here, but if to master computational thinking, you need to apply these. So that's decomposition just up here, abstraction, algorithms, and pattern recognition. So we're going to be covering decomposition and abstraction today. So what I'd like you to do is I'd like you to pause the video, write down these couple of sentences just here in your books or in a notepad, and then unpause the video, and we will then move on. Okay guys, welcome back. So abstraction, the first pillar we're going to be talking about. You tell me, what do you reckon abstraction is? I mean, this is a map here of the London Underground on the left, and this is a map what you've probably seen before on the right. What do you think abstraction is? Right, well, looking at this map on the left just here, this looks like a map for engineers, and this looks like a map for the public. Now, looking at this, I feel as though the public do not really care if they are going around a corner on some railway line. And all the public care about is what station they need to get off at on the tube. So here we've got straight lines. Here we've got corners. We've got a bit more information and detail. This is what abstraction is. It's cutting out the rubbish, cutting out the things you don't need, and making it much more simpler for people to understand and to understand the problem. So if you've got like a giant complex problem, you cut out all of the rubbish, cut out the stuff you don't actually need, and just focus on the basic thing you do need. I mean, when I'm on the London Underground, I do not care whether I'm going down, across, corner here, corner there. It's pointless. So therefore, abstraction's used in just London Underground pictures as well, as an example, to make it much more simpler for the public. Okay, so let's get down a definition of abstraction. I've got one just here. So we've got a really formal definition at the top, and what I want, and a definition that I just want in the back of your minds when you see the word abstraction, I want you to think of cutting out the rubbish. Cutting out the rubbish. Cutting out the rubbish, taking out the trash, the stuff that you just do not need. So we've got abstraction is removing unnecessary information. It is ignoring the characteristics we don't need and keeping the ones we do. So i.e. cutting out the rubbish. So in your books or notepads, can you please write down this top formal bullet point? And then underneath, I just want you to do equals cutting out the rubbish. Draw a dustbin if you need to. But abstraction is removing that information, so it's cutting out the rubbish. What's abstraction, you say? Cutting out the rubbish. All right, so pause the video, write down the notes, and then we'll come back. Okay, so I'm going to show you a real-world example of where abstraction can be used. So firstly, if I wanted to bake a cake and I've got the problem of making a cake, now there's loads of different types of cakes out there. I mean, you've got your vanilla, you've got your chocolate, you've got your carrot cake. So you've got tons and tons and tons and tons of different types of cake, but I just want to make a cake. So let's cut out the specific details of like a chocolate cake. You need to add your chocolate, you need to put some cherries on top, stuff like that. And let's just look at the general problem of making a cake. And it comes down to 4 or 3 kind of different things. So first up, you've got to have an oven temperature to actually bake the cake. You've got some ingredients of some kind. I mean, looking at these cakes here, they've got some different kind of ingredients. And then you've got some instructions to mix them together. So like mix your ingredients together. And then the final thing is to actually have a cooking time. So these are called general things because they apply to every single cake. You know, you're always going to preheat your oven to a certain temperature. You're always going to add some sort of ingredients and you're always going to have some sort of cooking time. The specifics to that, the specific details like, oh, you need to add chocolates or chocolate chip and stuff like that, it's not needed. We can cut out that rubbish of the specifics and just have the general information of making a cake. And so this is abstraction. This is where it can be used. In terms of like various systems and stuff, if you're making complex systems, you cut out the information and the specifics in those complex systems that you just do not need, hence cutting out the rubbish. So I've got a task for you guys, and it's basically abstracting information of a football team. It says, using the statements below, can you identify the ones that are useful, general patterns, and those that are not, specific details? In explaining the model of a football team. So let's have a look then. So let's have a look at a couple of specifics. So we've got Roy Hodgson is the England team manager. Now, this one would go in specific details because at the end of the day, Roy Hodgson is not a manager of every single football team. Just England is not anymore, but he used to be. It's just England's. And so therefore that would go in a specific and we wouldn't need that information. A general one would probably be a football team is made up of 11 players. Now, this is a general pattern because every single football team is made up of 11 players. And so we want to just cut out the specifics and keep the general patterns of a football team. So I've got some statements down here. Can you please copy out the table and write the statements in under general patterns and specific details if it's a specific or a general pattern. So the Roy Hodgson one, you'd write in under specific. And the England football, the football team is made up of 11 players. That would go under general. All right, guys, so pause the video, do this task, and come back and we'll go over the answers. Right, well done on that one. I hope you got on okay. Let's go through these generals and specifics. So Roy Hodgson is England team manager. We've done that one. He's not manager of every football team, so therefore it's a specific. And we've also done a football team is made up of 11 players. So this one is a general pattern. Right, let's have a look at the next one. A team is made up of a goalkeeper, defenders, midfielders, and forwards. Now, every single football team is made up of goalkeepers and so on. So therefore, this is a general pattern. Players wear a shirt, shorts, socks, and football boots. Now, every player has this, so therefore, it's a general pattern. Gareth Bale is a Welsh international footballer. Well, this is a specific. He's not every single kind of footballer, so that's a specific. Manchester United home kit is red. Well, that is specific to Manchester United. So, like various other football teams have different colours. So therefore, it's a specific. FC Barcelona play with one goalkeeper, 3 defenders, 4 midfielders, and 3 strikers. Well, this is a specific because that's just for Barcelona. You can have various other combinations. So that's a specific. And then a football team is run by a manager. Every football team is run by a manager. So therefore, it is a general. So give them a tick, mark it, and then we'll move back on. Right, so the next one is decomposition. And I want you guys to have a think about decomposition just by looking at this picture. You tell me, what do you think decomposition is? So have a think and take a look at the picture. All right, so I hope you're thinking that decomposition is breaking down a large problem into lots of different problems. I mean, if you look at the word decomposition, it's similar to the word decompose. Now, decompose, if you've got like vegetables in a bin, they're going to decompose and turn to compost if you've got compost stuff. So it's basically breaking, that decompose is breaking stuff down. Decomposition is breaking down problems. So breaking down large complex problems into smaller problems that are far more easily solved. So let's say you had to code a giant system for a school with registers, tracking grades, and student details, holding all of this information. You would want to use decomposition because that problem's massive to think of by itself. But then when you break it down into lots of different subproblems, it becomes a lot easier. So you could say, right, well, let's work on the register today, registration. Let's work on tracking today. Let's work on student details another day. This makes that problem a lot more easier. And then when you're working on like those student details, you can break that down even further. Oh, right, so we're going to store a student, the parent's email address. We're going to store the student's address and so on and so forth. And it becomes nice and simple to make some giant system and solve some giant problem. I bet you come across it in maths quite often where you have like some large formula that you need to break down in algebra and stuff like that. And when you've actually broken it down into smaller little problems, it becomes really easy to solve. It happens a lot when we're programming as well. So when I give you a big programming problem, a lot of people say at the start, oh, sir, I don't get it. What's going on? I don't understand. But then when you break it down to simple little steps like, oh, well, you print the user's name, you ask the user what their favorite color is. Oh, and then you need to say your favorite color is followed by their favorite color. It's broken down nice and simple and easy for you to do. So breaking down large complex problems into smaller problems that are far more easily solved. So can you guys please copy this sentence down and then come back? Okay, so I'm going to give you an example of a real world decomposition, and there's many ways you can do this, but this is just a very simple example. So for example, let's say our problem here is boiling milk, and we need to boil some milk. So let's break it down. Well, first up, we need to get some milk. So I've got milk with a cow in here. It could be go to the shop and get some milk, something like that, something nice and simple. And then what you need to do is you need to transfer that milk into the pan. You put on the gas and you boil your milk. Great. That's a nice simple problem of boiling milk broken down into much more simpler problems. So you can use decomposition to keep on breaking them down if you like. So like put on the gas could be push the hob in and turn the dial to various temperatures, stuff like that. You can break it down further if you wish, but nice and simply broken down is just that. Okay, so I've got a task for you guys. I want you to use decomposition to break down the problem of organising a party. So just like I've just done up here, so instead of boiling milk, yours is going to be organise a party. And I want you to think of some ideas of what you would need in order to host a fantastic party. All right, so pause the video, give it a go, and then we'll come back. Right, well, I'm going to do the solution with you guys. So what I'm going to do is I'm going to start off right here, and let's have a look. We are going to organise a party. Organise a party. Right, so first up, when we're organising a party, we're probably going to need some decorations. So let's have a look at decorations. We are probably going to need some food for our guests. And we are probably going to need to send out some invitations. And also we are probably going to need some music, or it would be quite a quiet party. So let's put some music here. All right, now you could just have that as a nice simple solution, or you could go into much more detail. So like you could have for decorations, you could have down here, get decorations. And then you could have place up decorations, and then food, you could have like buy food, cook food, put food out. Invitations, you can have buy some party invitations, get some stamps, put the invitations in an envelope, and then post invitations. And for music, you can have download various songs and stuff like that. But the main thing of organising a party is these top 4 ones just here, and then you can break them down even into smaller, easier problems as well. I hope you understand that. I hope that's okay. But decomposition, guys, is basically breaking down problems. Okay, our last and final definition is an algorithm. Now, if you've ever had any siblings in any older years and you ask them what an algorithm is, they should be able to tell you this because I've repeated it over and over and over again. This is the perfect definition for an algorithm. It reads, an algorithm is a finite sequence of instructions in order to solve a problem. Now, let's break this down. Let's use some decomposition and break this long, complex sentence down so it's nice and easy to understand. Finite. Now that is opposite of the word infinite. So infinite means that it goes on forever, so therefore finite means that it's going to stop at some point. You do not want to be dead by the time your algorithm is finished. It needs to end at some point, and it needs to stop in a reasonable amount of time. Sequence. Now, a sequence basically means in order. You run some instructions in order. So like when you don't put the cake mixture in the oven without actually making the cake mixture. So it needs to be in order. Instructions is basically to do something and to solve that problem. An algorithm is a finite sequence of instructions in order to solve a problem. An algorithm is a finite sequence of instructions in order to solve a problem. An algorithm is a finite sequence of instructions in order to solve a problem. Relate it back in your head. Algorithm is a finite sequence of instructions in order to solve a problem. Finite sequence of instructions in order to solve a problem. What's an algorithm? Finite sequence of instructions in order to solve a problem. Finite sequence of instructions in order to solve a problem. What I would like you to do, I'd like you to please copy down the sentence, an algorithm is a finite sequence of instructions in order to solve a problem, in your books, please, or in your notepads, and then we'll come back, answer an exam question, and then that's our lesson finished for today. Okay, welcome back. An algorithm is a finite sequence of instructions in order to solve a problem. I would like you to please, when you finish this lesson, go and tell every single person in your household that an algorithm is a finite sequence of instructions in order to solve a problem. Okay, so now it's time for an exam. So it says, Drive Sim Tutor is a 3D driving simulator program designed to allow learner drivers to practice following the highway code whilst driving through a virtual town. The simulator's developers study a real town. They then use abstraction, don't forget cutting out the rubbish, on their findings before designing a virtual town. So basically what this question is saying, that you've got some software and they're trying to mimic an actual town in order for somebody to learn how to drive. And let's have a look at the question. As a result of abstraction, there'll be similarities and differences between the real town. State 2 similarities there might be between the virtual and real town. Explain why these similarities exist. So basically what this question is asking is, you've got some software that's mimicking a town. What are the things that in real life is going to be the same inside of this software? I will give you one example, but I don't want you to use it in your answer. For example, the traffic lights will be the same, won't they? So when you come to a traffic light, it's going to work the same as it does in real life. And an example of that's not going to be in the town is Aunt Bessie down the road walking her dog. At the end of the day, you're not going to have specific Aunt Bessie in a program. You may have some people in there, but you're not going to have specific people in this virtual town. That's too specific. You're going to need to think of general similarities that are going to be the same. All right, so pause the video, answer this exam question, do time yourself. In lesson, I'll give you 4 minutes. So give yourself 4 minutes. You need to justify why they would be the same as well. All right, so pause the video, come back in 4 minutes. Off you go. All right, guys, welcome back. I hope you understood that. So let's have a look at some similarities. So first up, the road signs and road markings will be the same as well to mimic this town. So the user can practice obeying these rules when driving. So you would need to keep those road sign markings the same, because when they're actually driving in real life, they'll need to recognise them. Traffic lights, I gave you that one. So the user can practice obeying traffic light signals. Zebra crossing, so the user can practice slowing down / stopping at zebra crossings. Cars and vehicles, so user can practice driving with other cars on the road. Pedestrians, so user can practice looking out for and avoiding pedestrians. There's loads of other ones, guys. Just basically think of when you're if someone's learning how to drive, what they would need to know. All right, guys, so that's the end of part one. In part two, we're going to be looking at the insertion sort algorithm, and we're going to be learning steps and details of various algorithms. I hope you found everything okay. Any problems, as always, please do email me and let me know. All right, see you next week. Bye-bye.